Okay, so this is our last unit of the year. In this unit, in particularly this set of notes, is an introduction to what are called eigenvalues and eigenvectors. Okay, so what we're going to start off with here is some matrix that is square. It's an n by n matrix. And we're going to have a vector, and this vector is going to be an Rn. And what we want is to be able to say that A times this vector is some scalar times that vector. Now, if I can do that, then we call this an eigenvalue, and we call the x here an eigenvector. And these are unique. The eigenvalues are unique to A, and the vectors are also belong to A. So in value and a vector that solves this equation are called eigenvalues and eigenvectors. And sometimes, like when they're taken together, we call them an eigenpair. Okay, so let's take an example of this. So let's say I have some matrix. And we're going to take a really simple one here. This is 2, 0, 0, negative 1. Okay, and I'm going to let x1 be the vector 1, 0, and we're going to let x2 be the vector 0, 1. Okay, so if I take A times x1, I get 2, 0 times 0, negative 1 times 1, 0, which is, if you multiply that out, you're going to get 2, 0. Now, you're going to note that 2, 0, so like 2 times 1, 0 is 2, 0. Oops, 2, 0. There we go. This means that the vector x1 here is an eigenvector. And the corresponding eigenvalue here is going to be lambda 1, which is equal to 2, because A times x1 is the same as 2 times x1. Now, you can't do this with just any vector, and you can't do this with just any value. But for a given matrix, this is not necessarily unique. Okay, so let's take a look at this other vector I have hanging out here. So if I take A times x2, that's 2, 0, 0, negative 1, and this is times the vector 0, 1, and that happens to come out as 0, negative 1, which means that A times x2 is equal to negative 1 times 0, times x2. So this means also that x2 is an eigenvector, and negative 1, right? So if that's lambda 2, is an eigenvalue. Okay, so we get an idea of what these things are, right? And in all honesty, this matrix A actually only has two eigenvalues. It has an eigenvalue of 2 and an eigenvalue of negative 1. However, these eigenvectors are not the only eigenvectors. Let's dig a little bit deeper here. Okay, so we showed earlier that if I take this 2, 0, 0, negative 1 times 1, 0, I get 2, 0, right? So this told me that A times this vector 1, 0 was 2 times the vector 1, 0, which means this vector is an eigenvector. The 2 is an eigenvalue. Okay, fine, great, wonderful. But let's take a look at this case. Let's take 2, 0, 0, negative 1 and multiply this thing by negative 3, 0. And if I do that, I end up with negative 6, 0, which means that a times negative 3, 0 is the same as 2 times negative 3, 0. So 2 is still my eigenvalue, but I've also identified this as an eigenvector that corresponds to that eigenvalue. So these things taken together are what we call an eigenpair. So if you combine an eigenvalue with an eigenvector, it's called an eigenpair. But usually the set of eigenvalues that correspond to a particular eigenvector, the set of eigenvectors that correspond to a particular eigenvalue is usually an infinite set. And actually, we're going to prove in a minute here that that set is actually a subspace of Rn. Okay, so we're going to let A be some n by n matrix, right? N by n squared matrix. And we're going to let lambda is eigenvalue for A. Okay, so the argument here is that if I take the 0 vector, important note, the 0 vector is never considered an eigenvector. So by definition, eigenvectors are non-zero, okay? Note that well. So if I union the 0 vector with all of the vectors that are in Rn such that Ax is equal to lambda x, so all the vectors that solve the eigenequation with lambda, the argument here is that this is a subspace of Rn. We're going to call this an, you got it, eigenspace. Okay, so proving this is actually kind of simple because we know that Rn is a vector space, right? So what we got to do is we have to take two vectors, right, that are in Rn such that A times x1 is lambda x1 and A times x2 is equal to lambda x2, saying that they're eigenvectors that correspond to lambda. All right, and we're going to let C, of course, be some real number. So what do I have to prove here? I have to prove that I'm closed under addition and scalar multiplication. So if I take A times x1 plus x2, then I'm in the eigenspace if this works out to be lambda times x1 plus x2. Well, this is the same as ax1 plus ax2, which is lambda x1 plus lambda x2 from this, which is lambda times x1 plus x2, which means I'm closed under addition. Now, if I also have to prove closed under scalar multiplication, A times C times x1 is the same as C times ax1, which is C times lambda x1, which by the associative property is lambda times cx1, which means I'm also closed under scalar multiplication, which means I have a subspace. So eigenspaces are subspaces of Rn. All right, so the next game here is how do I find eigenvectors and eigenvalues? Okay, so to find eigenvectors and eigenvalues, we have to find things that solve this equation. Ax is equal to lambda x. Okay, so what we do here is we bring everything to one side. So we're going to say that lambda x minus ax is the 0 vector, right? All right, so if I pull the x vector out of this, I get lambda times the identity minus a times the x vector is 0. Now note, by the definition of an eigenvector, that vector cannot be 0. So this means that I have a homogeneous system of equations, right? Because this is some matrix. This is ax is equal to 0, right? We'll call it b. Bx is equal to 0. This is a homogeneous system of equations that has to, if that eigenvector exists, this thing has to have a non-zero solution, which means from all of these things that we've studied before, if I take the determinant of lambda I, the I times I minus a, I have to equal 0, because it means that I have non-zero solutions, which means that that matrix is not invertible, which means its determinant must be 0. All right, so this kind of gives me a bit of a theorem here. What we're going to say is, 1, if lambda is an eigenvalue, if and only if lambda times I n minus a is equal to 0. So this is an if and only if, so we'll call that number 1. And number 2, x is in the eigenspace determined by a and lambda, right? If and only if lambda times I minus a times x is equal to the 0 vector. All right, so useful things here. This equation right there, okay, we have a name for that. We're going to call this the characteristic equation. And this piece right there actually kind of works out to be a polynomial. So the determinant of lambda I minus a is going to give us something in the form of lambda to the n plus c sub n minus 1 times lambda to the n minus 1 plus, and then we keep going, to c sub 1 lambda plus c sub 0. This polynomial that's going to get worked out, because when I do the determinant here, I am going to get a polynomial where I get powers of lambda, is what we're going to call the characteristic polynomial of A. And we're going to leverage this information in order to first find eigenvalues and then find eigenvectors. Okay, so here we go. Okay, so let's take an example here. Let's take the example of 2, -12, 1, -5. All right, so the characteristic equation here, AI or lambda I minus a, right, is going to give me the determinant of that. Is going to give me the determinant of a lambda I is lambda 0, 0, lambda minus a, which is 2, -12, 1, -5, right? So this is the determinant of lambda minus 2 plus 12 minus 1 lambda plus 5. So we're going to take the determinant of that thing. Okay, so determinant here says multiply these, which is lambda minus 2 times lambda plus 5 minus, this is going to be plus 12, right? So that's lambda squared plus 3 lambda minus 10 plus 12 is lambda squared plus 3 lambda plus 2. So there is my characteristic polynomial. Now, if I set that characteristic polynomial equal to 0, which is what has to be true if lambda is an eigenvalue, then I get lambda plus 1 times lambda plus 2, which means my two possible eigenvalues are -1 and -2. I now have the eigenvalues that correspond to the matrix A. Okay, so a quick note. This is where MATLAB can be particularly useful. Okay, so let's put in that matrix that we just did. 2, -12, 1, -5. There's my matrix. EIG is the eigenvalue function in MATLAB. So if I take the eigenvalue of A, it returns to me -1 and 2. So there you go. Really quick way to find the eigenvalues of that particular matrix. So now we have to find the set of vectors that correspond to each of these eigenvalues. So let's start with the lambda equals -1. All right, so if this is true, then -1 times lambda minus A should equal, well, that's going to be -1 minus 2, -1, 12, -1 plus 5, which works out to be -3, 12, -1, 4. Now note, eigenvectors are things that solve the equation lambda I minus A x equals 0. So this is a system of equations, so I can make an augmented matrix, put zeros in here, use Gauss-Jordan, comes back with 1, -4, 0, 0, 0, 0, which is an infinite set of vectors that I expect, right? Let x sub 2 be t. That forces x sub 1 to be 4t, which means any vector in the form of 4, 1 times t, where t does not equal 0, is an eigenvector that corresponds to the eigenvalue -1. All right, so you can also play this same game with the other eigenvalue, which is 2, and you're going to get the lambda I minus A in this case will be -4, 12, -1, 3. Gauss-Jordan, -4, 12, -1, 3, 0, 0 gets me to 1, -3, 0, 0, 0, 0, which means that if I make x2 equal to t, then x1 has to be 3t. So x is any vector that is 3, 1 times t. Okay, so this is the set of all eigenvectors that go with the eigenvalue 2. Okay, so again, a quick MATLAB note here. Let's go back to the MATLAB screen here. All right, so we're going to use that same, I'm going to CLC, right? So we have A as being this matrix. The Eig function can also be overloaded. So let me make my window a little bit bigger here. Okay, so I'm going to ask for VD. So this is going to be a matrix VD is going to be Eig. So it's the same command on A. So this is an overloaded function. If you just ask for Eig A, it gives you the two eigenvalues. Here I'm going to get two matrices, okay? The D matrix is a diagonal matrix where the eigenvalues are on the diagonal. The V matrix is actually the columns of the V matrix, when I do this, are the corresponding eigenvectors. So this eigenvector 9, this first column, sorry, the column, can't highlight the column there. So this with the 0.9701, 0.2425 is an eigenvector that corresponds to -1. The other is an eigenvector that corresponds to -2. Now these are not as neat as the ones that we had, but if I show you something here, these are actually unit vectors that are corresponding to those sets. So like if I take and make a vector, let's call it, I don't know, G, right? Where I take the 1, 1 element of V, and then I take the 2, 1 element of V, and I norm G, you see that it has a magnitude of 1. So that's a unit vector. Now the trick is like, okay, so if that's the unit vector, then how do I get to see this as like the vectors that I found? Because like the vector that I found corresponding to -1 said it was a multiple of 3, 1, right? So like if I think about this, if I want the 1 in the second position there, I should take G, right? And, well, I should multiply 1 dot divide V 2, 1, right? So that would be the 0.2425, right? And then multiply that result, so let's put parentheses around that, times G. And I think that that will make the second term into 1. And by scaling that, hopefully it should make the first term into 3. Oh, sorry. 3, 1 is not the one that corresponds to -1. The 3, 1 corresponds to the 2. So this actually corresponds to the 4, 1 is the -1. All right, so like if I look again, play this out again. So like here's my two resulting vectors. And now let's make H the second column, right? So H is going to be V 1, 2 side by side with V 2, 2, right? So that's the second column of V is now as a row vector. And then remember, if I take norm of H here, I should expect that this is 1. And if I take 1 dot divide V 2, 2, right? Let's take that whole quantity times H. This should give me the 3, 1. There it is. So there's the two vectors that I was expecting. So just to kind of show you that MATLAB, though it's giving you like funky answers because it's giving you unit vectors instead of the ones that you would get by doing parameterization, they are the same set of vectors. They scale into each other. Okay, so let's go back to our thinking. Okay, so there's a last little bit here. If you happen to have a triangular matrix, something like 2, 0, 0, -1, 1, 0, 5, 3, 3, sorry, 5, 3, -3. This is a triangular matrix. We're going to leave this as an unproven theorem, but the elements that are going down the diagonal of a triangular matrix, so lambda equals 2, lambda equals 1, 1, not -1, lambda equals 1, and lambda here equals -3. These are the eigenvalues of that matrix. So if you have a triangular matrix, either upper or lower or diagonal, the eigenvalues are going down the diagonal of the matrix. With a little bit of work, you can see that lambda equals -3 is going to correspond to the vectors where you take 0, 0, 1 times a scalar. Lambda is equal to 1 is going to correspond to the eigenvectors where you take 0, 4, 3 times a scalar, and lambda is equal to 2 is going to correspond to the vectors where you take 5, -5, 2 times a scalar. So this is kind of a pathway that's going to be useful. If you have the diagonalized or a diagonalized matrix or a matrix in the triangular form, the elements that go down the diagonal end up being the eigenvalues. And ultimately, without doing a whole lot of work, you should be able to come up with the eigenvectors that correspond to them. All right, so this is a bit of a lengthy recording, but it's giving us a jump start on eigenvectors and eigenvalues.